Hello, everyone, and welcome to today's webinar. I'm Jamie Funnell, a longevity actuary at Pension Insurance Corporation and current chair of the CMI Annuities Committee. And I'll shortly be handing over to Professor George Streftaris and Dr. Isa Arick of Heriot-Watt University to take you through their recent work on modelling cancer risk. This work is detailed in two recently published papers, links to which are available on the webinar registration page and will be available on the webinar series webpage after the event. So this 1 hour session will provide a detailed assessment of the variation of cancer incidence and mortality by region and socioeconomic status. On top of this, it will explore the impact on cancer mortality by the average age at diagnosis, something which is particularly relevant given the delays across the NHS as a result of the COVID-19 pandemic. Once again, this work has been enabled by the Actuarial Research Centre, which supports actuarial researchers around the world to deliver cutting-edge research addressing some of the most significant challenges in actuarial science. So a few housekeeping points before I hand over. The presentation will last around 40 minutes with 15 minutes or so at the end allocated to questions and answers. You can submit your questions as we go along using the Zoom Q&A function, and we will do our best to address as many of these as possible at the end. You cannot be seen or heard, and the chat function is also disabled for the duration of the session. The webinar is being recorded, so you will have a chance to catch up on anything you miss. And finally, as a reminder of those of you that need CPD, this can be logged in the usual way. So without further ado, I'll hand over to Professor George Streftaris to help us all to better understand cancer risk.
Okay, Jamie, thanks very much for the introduction. So I will start this this presentation, and then I will hand over later on to Isa. So to start with, let me just say a few words about the project of which part this work forms. It's a bigger research program led by Professor Andrew Kearns at Heriot-Watt University. The theme, well, the topic of the project is modeling, measurement, sorry, I cannot see my screen here. It's about longevity and morbidity risk. Apologies for that. So as Jamie said before, the project itself, the bigger project, is funded by the Actuarial Research Centre of the Institute and Faculty of Actuaries, and we also have additional funding, especially for the work that I'm going to talk about today, from the Society of Actuaries in the US and the Canadian Institute of Actuaries. There's a number of themes in that project. But the work I'm going to present today, the work that myself and Isa are involved in, is the theme that you can see at the bottom of your screen there, the stochastic models for critical illness insurance. And this is also joint work with Erangel Dodd at Southampton University, and as I mentioned, with Professor Andrew Kearns. So just to motivate the work a little bit, just to mention what were the research objectives, the research aims when we first started this work. Well, to start with, we focus on cancer rates, both morbidity incidence cancer rates and mortality cancer rates. We looked at all cancers together, but then we also looked at separately at lung cancer, bowel cancer, prostate and breast cancer rates as well. So the main aim of the work was to look at how these rates change with time, if there are time trends, but most importantly, to see whether or not there's variation, there are differences between different regions in England and between different deprivation groups. We also, perhaps a bit later on, after we started the project, we started looking at how we can quantify the impact of diagnosis delays on mortality from cancer. And this was also motivated from obviously a very contemporary topic, COVID-19, which has delayed diagnosis of cancer. We also wanted to look at how cancer rates can change in the future. So towards the end, Isa will be talking about projection of cancer rates as well. Let me just say a little bit about the data that we had or have available for this work. It's data on cancer cases, cancer registration cases, and deaths from cancer. The data concern England only, and they come from, they were provided from the Office for National Statistics. So in the data, we have information on age, and age in our data comes in groups of 5 years, 1 to 4, 5 to 9, and so on. Having said that, the results that I'm going to show today, to talk about today, most of them will be age standardized results. So we standardize across all ages, and we do that using the European Standard Population from 2015. We also have information on gender. We have calendar year, mainly for the analysis, for the results, for the findings I'm going to show you today. Most of them, we're using data from 2001 up to 2017. We also have data for some of our work from going back to 1981, and also more recently data for 2018 for some of the work that we have done. We also have information on income deprivation. So you will see that as ID on some of my slides. So we have the deciles, the 10 deciles for income deprivation, starting from decile 1, the most deprived, going down to 10, decile 10 for the least deprived. And we also have different regions in England, the main regions in England, starting from the north, northeast, northwest, down to southeast and southwest. Okay, so let me start by showing you some results about the trend over time for cancer incidence and mortality, actually, on this graph. So what you can see on the graph is incidence and mortality rates for all cancer types. It's age standardized rates, as I mentioned before. And the rates you can see here do not involve any modeling. These are what we call the crude or raw rates, if you like. So on the horizontal axis, you can see year time going, in this case, from 1981 to 2017. And on the vertical axis, we have the incidence, the rate, incidence and mortality rate. So the main thing in this graph is that actually you can see that, well, you have different colors there. The light blue is for males, dark blue for females. Both morbidity, well, rates for both males and females are increasing, the morbidity rates, whereas the mortality rates, again, both for males and females are actually decreasing over time. And this is good news about the mortality rates. Mortality rates decreasing is definitely good news. Perhaps on the morbidity rates, you can see that there's a bit of a leveling off in most recent years, but that's something we need to perhaps investigate more with more recent data. Similar graph now for lung cancer. This is now an exception to what I was saying before, the general trend that we saw before on the previous slide. You can see that for males, the light blue lines, both morbidity and mortality is actually dropping for lung cancer, whereas for females, these two lines here, morbidity is definitely increasing. Mortality perhaps is a bit is leveling off in most recent years, but there's definitely a difference in the trends between men and women for lung cancer. And I think this will probably come up later on. This is most probably related to smoking habits. Okay, so as I said before, the main aim of this work was to look into the regional and socioeconomic deprivation differences. And the questions we were asking ourselves when we started this work is, well, mainly the two questions here, how big is the gap, if there is a gap between, let's say, the different regions or different deprivation groups, how big is that gap, and is it getting worse or better with time? And to answer these questions, we definitely need modeling, stochastic modeling, as I'm going to say in a minute. If you want just one reason for that, if I wanted to give you one reason for that, that would be to account for uncertainty in the data, in the models themselves, and so on. Okay, so that's the basic, that's a graph, if you like, a sketch of the basic stochastic model that we have here. So we have people moving from a healthy state into a diagnosed with cancer state. And that transition happens at rate theta, where theta itself depends on gender, region, age, deprivation, and time. So these are the 5 main risk factors that we have in this analysis. So as I said before, we want to build this model so that we can also quantify the uncertainty, and this will happen mostly through probability intervals, that what most of us know as confidence or credible intervals, depending on your approach to statistics. Right, this is the most mathematical slide I'm going to show you, so I promise. Just to highlight a couple of things. First of all, the model that we are using here is a Poisson model. It's not a Markov model. Perhaps the slide that I had previously, that I showed you previously, reminded some of you of a Markov model. Aisha is going to show you a more elaborate and complex Markov model later on. But this here is a Poisson model, where we're saying that the cases of cancer depend on the rate, theta, and E here is the exposure for each group that we consider. There's more complexity in this model. The theta, the rate itself, follows a given distribution, a log normal distribution here. And the main aim of doing that is to allow for over dispersion in the model. So we allow for more variation than you would normally find in a homogeneous population. We don't have a homogeneous population here. And on top of that, we have a Bayesian approach, a Bayesian model, where the risk factors depend on, well, we have a linear predictor for the risk factors, and the betas are the coefficients, the parameters, if you like, for those risk factors. The thing to keep from here is perhaps that we use vague priors for these risk factors, meaning that within our approach, we don't assume that we know much about what the impact of those factors is before we do the analysis. A little bit more on modeling. In addition, what we did was to, well, what we call here model selection or variable selection. So we wanted to find the model that describes the data in the best possible way. And there's statistical ways to do that using what I call here model fitting criteria, the marginal likelihood, the deviance information criterion, and so on. But the main, again, the main outcome of that was that all main variables, the 5 that I mentioned before, age, time, deprivation, gender, and region, these were important for all cancer rates and for lifestyle cancer rates, such as lung cancer, for example. What we also found, and we'll come to some more details about this later on, was that deprivation was not an important factor for non-lifestyle cancers, if you like, the breast and prostate cancer mortality, for example. Final slide about modeling. We also allow our model to, and our analysis to represent sudden changes in the trend of the rates, and we do that using the change, so-called change point analysis in statistics. Mainly, we want to allow, as I said, for sudden changes. For example, when a new intervention policy is introduced, some health or screening policy is introduced in the population, or after a certain age where we know from the literature that big changes actually can happen in cancer rates. So we do that again using statistical criteria, the BIC, for example. Mainly what that means is that we have a model which can have a single coefficient for the time parameter, for the time impact, if you like, or a model where the slope of the rates is actually changing from one year to the next year, from 2006 to 2007, for example. And we choose between those two models, as I said, using certain criteria. I'll just give you very briefly the main outcomes about age and time. So what we found, and perhaps you could see that from the very first slides that I showed you. So what we found was that age is a significant, has a significant effect, higher rates for older ages. Time, calendar time was also significant. In most cases, for most cancer types, we have higher incidence of cancer in more recent years, and we have lower mortality in more recent years. Gender is an important factor with higher rates for men, if we're talking about all cancers. But as I said before, again, let's look in more detail at what is happening with region and deprivation. And I think that's a good time to ask you a question, our audience. So here's the poll of the day. So if we're looking at the impact of income deprivation on lung cancer incidence for women, so that's, you can see that at the top of the screen there. So my question to you is, if we assume that there's a difference between the rates for most and least deprived, so this is about deprivation, this difference is it small, A, negligible, mostly noise, or B, is it significant with higher rates for most deprived groups in the population and getting wider with time, over time? Or is it C, significant, again, with higher rates for most deprived, but getting narrower with time? So things are getting perhaps better with time in terms of that difference. So I'll leave that question with you for a couple of slides time. I will talk about the regional, the effect of region first, and then I will come back to this in a few minutes. So let's look at regional variation for lung cancer women in 2017. So now I'm looking for at one particular year. You can see the map of England there, the 9 regions in different shades. So the different shades themselves represent different rates, different incidence rates for lung cancer. These are rates per 10,000, and the darker the shade, the higher the incidence rate. And we can see from the shading there that there's perhaps a divide between north and south. Incidence rates for lung cancer for women seems to be higher in the north as compared to the south. What we also did with this analysis is we quantified actually those differences, if you like, by looking at the regional effect compared to the average for the whole country. So if we're looking at Northeast here, Northeast has 40% higher rates than average, whereas Southwest has 18% lower rates than average for lung cancer lung cancer incidence. London about here is almost on average actually. We can look at a similar graph for this one for breast cancer now. So the first thing perhaps we notice on this map now is that the whole map is darker. So the shades are darker, meaning that the breast cancer rates are higher than lung cancer that we looked at before. Indeed, breast cancer is the most prevalent, perhaps, cancer for women in England. And the other thing we notice here is that the regional variation now is much smaller than for what we had earlier for lung cancer. You can see that the shades are more similar than before. Remember, breast cancer that we're looking at here is not a lifestyle, is not considered to be a lifestyle cancer. Right, and now it's time to answer the poll question. So we're now looking at deprivation differences. Let me describe what I have on the I can see that most of you have answered B, actually, which is the right answer. Let me show you why. That's good. Well done, everybody. So let me describe what we have on this graph. So we have 9 different plots, if you like. Each plot corresponds to a single region. So this one here is Northeast. On the x-axis, on the horizontal axis, is time in calendar year, and on the y-axis we have the incidence rates for lung cancer for women. Also, on each plot we have 10 different curves, and each of those curves represents a deprivation group, 1 to 10. Remember, 1 is most deprived, 10 is the least deprived. So what we can see actually on all of these graphs, on all the regions, is that we have the highest rates are for the most deprived, significantly higher. You can see the differences from the most deprived going down to these, deprivation group 2 and so on, down to the least deprived at the bottom of each graph. And then if we look at the gap, so let's look at Northeast, the gap here in 2001 between most and least deprived, and the gap in 2017 between those 2 groups. Unfortunately, that gap is getting wider. Things are getting worse in terms of the differences, deprivation differences for lung cancer incidence for females. So correct answer there was B. Let me also look at the same sort of topic, if you like, the same sort of question in some more detail. So again, we're looking at differences between most and least deprived rates for most and least deprived for lung cancer incidence for females. So in this graph now, on the y-axis, on the vertical axis, we have the rates for the least deprived. On the horizontal axis, we have the rates for the most deprived. The rates are per 100,000 on this graph. And you can also see this red line. This is what we call here the equality line. This is, well, before I say that, so on this graph, on this map, the little dots that you can see on the right-hand side are the different regions of England. So if the rates for least deprived and most deprived were more or less equal, more or less the same, you would expect all these regions to be very close to that equality line. So this is the X equals Y line, if you like, in this graph. The further you move to the right on this graph, then the further, well, the higher that the rates are for the most deprived. So for lung cancer, London is here, lung cancer for women. London is here, that's about 2.5 times higher. So rates for the most deprived are about 2.5 times higher than the rates for the least deprived. And things get worse as you move north. If you go to the northeast, 3.5 northeast is here. So the rates in the northeast, the rates for the most deprived are about 3.5 times higher than the rates for the least deprived. And obviously, as I've mentioned already, there's regional variation here as well. You can see that different regions, this factor of 2.5, 3.5, and so on is different between different regions. And well, let's contrast that to breast cancer. So the same type of graph now for breast cancer in the same year. Equality line here, the red one. Now we can see that the rates for the least deprived are actually higher. The ratio, if you like, most divided by least is about 0.8. The difference is not as big. The ratio, if you like, is not as big as on the previous slide, 2.5 or 3.5 and so on. It's 0.8 here. But definitely what we have is higher rates now for the least deprived. Remember again, breast cancer is not a lifestyle cancer. The other thing we're seeing here is that there's no regional variation. All actually regions lie on a line, if you like, meaning that this ratio is about the same for all the regions. Right, I think I am actually ready to hand over to Aisha, who's going to talk to you about mortality now, concentrating on mortality. So Aisha, over to you whenever you're ready there.
Good afternoon. I'm honored to give the rest of this talk, and I must thank for the opportunity. I will be continuing with cancer mortality risk, and what we'll be focusing on is deprivation and regional differences in type-specific cancer risks, specifically among leading cancer risks. And we also be looking into the impact of diagnostic delays on these cancer mortality rates. Moreover, we looked into the projection of cancer risks, some of them, and we'll be specifically talking about lung cancer mortality projection as part of this presentation. Before getting started, I must also say that our main results are based on fitted cancer mortality rates, where we used a similar type of Bayesian hierarchical model described earlier in cancer morbidity part. So let me get started. In this slide, what we are looking at is lung cancer mortality in women, specifically in 2017. In this figure, we are showing deprivation and regional inequality in a different way than the other previous figures. What we are looking at is deprivation deciles on the x-axis from 1 to 10, where 1 is showing the most deprived decile and 10 is showing the least deprived decile. And we are also seeing the 8 standardized fitted mortality rates per 100,000 people on the y-axis. And in this figure, we are seeing the most deprived decile is showing us the highest, biggest regional gap, whereas the least deprived decile is showing us the smallest regional inequality. When we move from 1 to 10, it is just getting much smaller. And in a similar manner with lung cancer incidence, we are seeing the highest rates in the most deprived decile. The following figure is related to breast cancer mortality in 2017, once again. Different than other cancer types, breast cancer mortality is not showing deprivation inequality. More accurately, deprivation variable is not found statistically significant to explain change in breast cancer mortality. That's why this map is showing us the rates in different regions of England only. And here, what we observe is less regional variation, as it happened in breast cancer incidence as well. And this is quite different than lung cancer mortality, as we noticed. And here, now we can start to look into the impact of diagnostic delays on type-specific cancer mortality, which is relevant to COVID-19 pandemic, actually. And as it is mentioned earlier, we actually have one additional variable in each cancer mortality model, what we call average age at diagnosis, denoted by AAD. And this variable is obtained using each type-specific cancer morbidity model. And for this sake, we are using a couple of formulas, as you might see at the bottom of this slide. The first formula is using the type-specific fitted cancer morbidity rate, and we are using the standard population as a weight in this formula. And what we obtain is average age at diagnosis split by year, deprivation, gender, and region. By applying the second formula, we are actually dropping the year level, and for this sake, we are using the original exposure denoted by E as another weight. And in this way, we actually hoped to quantify the impact of age at diagnosis on type-specific cancer mortality, which could allow us to quantify the impact of diagnostic delays on each cancer mortality model as well, since diagnostic delays became quite a big concern during the national lockdowns. We have a couple of figures related to this topic, and the first one is related to all cancer mortality in males. And in this figure, what we are looking at the impact of change in age at diagnosis on all cancer mortality in males in different regions of England. And the figure itself is showing the change in all cancer mortality in males on the x-axis. And what we see on the y-axis is the rates with confidence intervals, and there is this red vertical line which is showing us the mean level. According to this figure, what we can tell is, for instance, in the northwest of England, we have a lower effect compared to the mean level as a response, an increase in age at diagnosis on all cancer mortality in males. However, we observe a higher effect in the east of England as a change, as an increase in age at diagnosis. And London happens to show us an impact around the average here. The following figure is showing us the impact of diagnostic delays on all on lung cancer mortality in women. Here we have a couple of scenarios. One is related to impact of 6-month delay, and the other one is related to the impact of 12-month delay in lung cancer diagnosis. And here on the x-axis, what we are looking at is an increase in lung cancer mortality in percentage terms too. And again, the outputs are for each region of England with confidence intervals. Here, as a result of 6-month delay in lung cancer diagnosis, we see an increase around 3.5% in lung cancer mortality in each region of England, whereas we could observe an increase around 7% in lung cancer mortality as a delay around a year in cancer diagnosis, which is worrying. And here, London is showing us the highest impact among all regions. So from this slide onwards, I will be showing the results of an ongoing study. And we will be continuing to look at the impact of diagnostic delays on cancer mortality. What we'll be talking about is breast cancer mortality in particular. And here we are looking at this calculation from a different angle using a Markov model. What we see here is an illness death model, including 7 different states. And state 0, healthy, is the initial state. And we have 2 observing states, state 5 and state 6, which are associated to death because of other reason and death because of breast cancer. We have 4 additional states in the middle, as you might notice, and these are showing us breast cancer cases as diagnosed or undiagnosed with early or advanced stage breast cancer. If we have a closer look, what we see is all new breast cancer cases appear in stage 1, and we assume some of them would be diagnosed with an early stage breast cancer by entering into stage 3. And some others are assumed to remain as undiagnosed and develop an advanced stage breast cancer, and these are presented in stage 2. Women either in stage 2 or stage 3 are reckoned to enter into stage 4 by either developing an advanced stage cancer if they were in stage 3 or by being diagnosed if they were in stage 2. And last but importantly, we can see that death because of cancer, breast cancer, is only possible if the person is in stage 4. In other words, death is only possible because of breast cancer if the person is diagnosed with breast cancer and having an advanced stage cancer simultaneously. Because of time limitation, it's not possible to go through the whole details regarding how to describe these transition intensities from one state to another. However, I will be talking through the main assumptions along with the details of our illustration in the following couple of slides. Let's start with this one. Our illustration is based on a cohort of 100,000 women aged 47 at time 0, and you might consider time 0 as January 2020 if you wish. In this illustration, there is no projection involved, and we are making use of a limited number of data. One of the data we are using are related to breast cancer registrations and deaths obtained from the ONS, and these are used in the base scenario. In addition to these data, we also have weekly excess deaths in women between April 2020 and July 2021. This is provided by Public Health England, and this is also publicly available data, different than the others. We are making use of these data on COVID-related scenarios. If you look at the timeline just above, you might see how we calibrate the model by thinking of the cohort under inspection. We are using the data in 2001 to describe transition rates at age 47, and we are using the data in 2006 to describe the transition intensities at age 52 and so on. In this way, we are defining the rates in each 5-year time interval, and we assume that the rates would be changing linearly from one age group to another in each 5-year time interval. We have further two assumptions, and these are all informed by the literature. The first main assumption is related to ONS data, publicly available ONS data between 2012 and 2016, which is telling us nearly 70% of all breast cancer registrations are diagnosed at early stage. And this assumption is affecting transition intensities involving states 2, 3, and 4. We have another assumption informed by the literature, which is about 30% of breast cancer cases with an early stage cancer could, or more accurately, would develop an advanced stage cancer later on. And this information is affecting transition intensities involving state 4. We have some further assumptions in this slide, and these are specific to COVID-related scenarios. To start with, we assume that breast cancer cases wouldn't be changing. They would be equal to the one in the base scenario. And what I'm talking about, the cases in state 1. So in this way, we are assuming that the pandemic wouldn't have a direct effect on breast cancer cases to accelerate the breast cancer cases, in other words. And we have a couple of scenarios in COVID-related scenarios. These are specifically related to the reduction of cancer registrations. And here, what we assume is there would be a decrease around 75% for 3 months, specifically between April and June 2020 in the first scenario. And after this 3 months, we are assuming cancer registrations would be returning back to the pre-pandemic levels. And in scenario 2, in addition to this assumption, we further assume that the slowdown in cancer registrations could continue for another 9 months in total. And particularly, there would be a decrease of around 50% between July and September 2020. And then there would be another decrease of around 25% for the following 6 months before returning back to the pre-pandemic levels. One last assumption is related to one published Public Health England study. This is done in 2017. And here we assume nearly 4% of all excess deaths could be related to breast cancer deaths. And this assumption is affecting transition intensities involving stage 6, which is the death because of breast cancer. Finally, we have a chance to see some numbers. In this table, we tabulated a number of people in selected states, specifically in healthy state, along with death-related states. And what we see here is the number of people at the end of 20 years when they reach age 67. We have 2 main conclusions where I will be talking about scenario 2 by making a comparison between this scenario and the base scenario. The first main conclusion is related to excess number of deaths, which is the difference between death numbers in scenario 2 and the base scenario. If you look at the first number here, what we see is 25, which is showing us the excess number of deaths because of breast cancer. And it shows or indicates an increase around 4% compared to the base scenario. And notice that this number is the difference between 670 and 645. And the excess number of deaths due to other reason would be equal to 732 if scenario 2 could have happened. And this is showing us an increase around 19%. The second main conclusion is related to 10-year net survival rate, where we define the net survival by not entering into any of death-related states. We have two outcomes here. These are related for a woman aged 47 with an early or advanced stage breast cancer. And what I will be talking about is the 10-year net survival rate for a woman aged 47 with an advanced stage breast cancer. This is because the impact is more dramatic here. And you might notice in this case, 10-year net survival rate would be dropping from 19% to 15.7%. This impact could be more severe if you could consider older age groups. This is because of the impact of the pandemic at those age groups, and also these people could be more vulnerable to having cancer. Now, let me just briefly talk about our projection results, which is the last part of this presentation. We have looked into projection of some cancer risks. Here, this setting is applied. This setting you see here is applied to lung cancer mortality. And we applied this setting separately for women and men. This setting itself is quite similar to our earlier Bayesian hierarchical setting. There is two main differences there. The first main difference is coming into the location parameter of log normal distribution, where we introduce the location parameter by using the main variables only. And when I say main variables, what I'm referring as age, period, region, and deprivation variables. And you might see each one of them is introduced as a categorical variable. And in addition to these, we are also making use of average age at diagnosis, which was an input we found significant to explain lung cancer mortality earlier on. Different from the other variables, though, average age at diagnosis comes into the model as a numerical variable, and it is also split by region and deprivation, which can be considered as a kind of indicator in the model. The second main difference is coming with the period effect. So we are introducing the period effect in the model by using a random walk weight drift. And in this line of the work, we are using a couple of normal distributions attributed to drift component and error term in the period effect. Later, we are also using another inverse gamma distribution to define the variance of the normal distribution. So we have a couple of figures related to this model. And the first one, more accurately, is related to lung cancer mortality in men at age 72. And here what we see is the lung cancer mortality over the years from 2001 till 2035. The projection is starting from 2019 onwards, and the projection results are shown as dashed lines, whereas we see the fitted rates as solid lines before 2019. We are looking at different deprivation deciles, including the most and least deprived deciles in the northwest, London, and the southwest of England. The main thing here is that we have a decreasing trend in each deprivation deciles of each region of England. However, if you look at the projected rates in the most and least deprived deciles, we see that these are not catching up even at the end of the projection period. If you look at the similar figures for women at same age group in the same deprivation deciles of the same regions of England, what we see here is that, well, first, we don't have a decreasing trend. The rates are, how to say it, leveled up, if not increasing, in different deprivation deciles, and there is more uncertainty here. But in a similar manner with male ones, what we also see is that the projected rates in the most and least deprived deciles are not overlapping by staying significantly different at the end of the projection period. So both main figures are showing us a persistent deprivation gap. So let me conclude the presentation by saying a few more words. In the whole study, what we see is there is a deprivation gap, there is a widening deprivation gap in cancer risk among different regions of England, but this is not for all cancer types, but this is mostly related to lifestyle cancer types. And we also found that delays in cancer diagnosis could have significant consequences, severe consequences, by increasing type-specific cancer mortality more than we expected. And as I just mentioned, we observed a persistent deprivation gap, at least in lung cancer mortality, when we looked into the projection results. There are more things to do, and there are more things to do, and these involve, for instance, to answer questions such as what the potential implications are for related insurance products, such as critical illness insurance, and whether it would worth to consider health interventions at regional and deprivation levels to prevent more deaths or higher incidences or in England. So I must thank for your patience, and I would like to say that you might find more details, discussions in the published studies, and please feel free to reach us out whenever you would like. And thank you. Now we can accept questions and comments. Thank you.
Thanks very much to you both for that. It was very, very interesting and enlightening. We have had lots of questions coming in, so do keep them coming in. But yeah, let's crack on with the Q&A. So I think the first one is just asking sort of for a bit of clarity over the data. So they've asked, when you say you have income deprivation by decile, sort of what specifically do you mean by that?
Well, let me start this, and Aisha, I'm sure you will have some comments as well. So this is, I'm looking at the question as well. Is that for each cancer case? Yes, exactly. That's income deprivation is measured actually on a much, we have regions in our analysis, but we also have income deprivation measured at a much finer scale, at a local scale, using the LSOAs, the lower output areas. Can't remember the exact acronym there. So for each case, for each group, actually, yes, we do have on that scale the deprivation decile. So if that group is actually on the top 10% or the next 10% in terms of deprivation, income deprivation, and so on.
Great, thank you. So yeah, the next one is just asking whether you have done the lung cancer comparison by deprivation decile for males and see a similar widening of the gap over time as the female results show us.
Right, okay, let me start with that, and then I will ask Aisha to tell us about mortality as well. I think we've shown you here both, well, some results for incidence, morbidity, and then some results towards the end for mortality. So the story is similar, but not exactly the same, I think, for morbidity and mortality. I think the general, if I had to give a very quick answer to this question, is that the trends are different for men and women for lung cancer, but the differences are smaller as well. So the gap, if we're looking at males, lung cancer, the gap between different deprivation groups is definitely, well, is smaller than that compared than that for women. And that's the case. It is still increasing, but it's smaller for men. And that's the case for morbidity, for incidence. I don't know, Aisha, if you can tell us a little bit more about mortality then for these rates.
So mortality rates are decreasing for males, but in line with deprivation gaps, they are much smaller, but still widening, if I'm not wrong. Yeah.
Okay, wonderful. So this next question is quite involved, a bit long, but I'm just going to read it out verbatim to you, but you may be able to read it as well. But so the cancer incidence rates for regions use the same age standardized population. Therefore, differences between the regions for breast cancer might be down to different actual age distributions between the regions. So in particular, if cancer rates increase with age, the difference between London with lots of young people and the Southwest with lots of pensioners might be caused by this. Is that fair?
I think that's a good point. I think when you look at what we have looked at in this talk, mostly age standardized rates, you do lose a lot of information in between about what happens in specific ages, especially where you have different cancer types, where the distribution, the age distribution for certain cancer types will be different. I think that's also a good point in terms of what is happening in London, because I think the demographics there and the diversity in the population in London makes a lot of makes an interesting story there, because I think in many perhaps I didn't say much during the presentation, but London in many cases stands out as an interesting case, either very low or very high rates, or different than the rest of England. So yes, I think again my answer would be that if you're looking at specific ages, then you would see some of these differences being different. And again, that would be also the case for different types of cancer, where the distribution of the age distribution would also be would be different. I think there are advantages into looking into age standardized rates, as we have done in this presentation. But yes, if you then want to make, for example, if you're involved in policy and you want to look at and target specific age groups or screening programs for specific age groups, then looking at the particular age rates for particular ages, that would be very, very important as well.
Great, thank you. Have you looked at the conditional probability of cancer death given cancer diagnosis? And in this conditional setting, is deprivation an important factor for breast cancer mortality?
Right, that's a very good question. I think my quick answer would be, have we looked at it yet? Well, no and yes. No, in the sense that we haven't explicitly looked at it. We haven't calculated conditional probabilities, I think. Aisha would correct me if I'm wrong. She's more familiar, I guess, with the details.
No, we haven't looked into that one. But by the way, I'm seeing the question, and it starts with deprivation is not an important factor for both breast cancer morbidity and mortality. And actually, it is not. I'm not sure if I'm confusing myself, but deprivation is not important for breast and prostate cancer mortality, but these are important for morbidity, cancer morbidity and prostate cancer morbidity. We haven't looked into that probability you mentioned, but we will be looking as part of the Markov model later on.
Yeah, and just to add to that, so what I'm thinking is, when I say that we haven't, but maybe have looked at this a little bit, is that we definitely haven't looked at it explicitly to calculate those conditional distributions and so on, conditional probabilities. But we, in the second part of today's presentation, when I presented this impact of delays in diagnosis delays on mortality, that's exactly what we were trying to do. We were trying to see, perhaps not exactly as what the question asks there, but we were trying to see how these how diagnosis or later diagnosis actually affects mortality. And I guess most of us would probably intuitively say, yes, it does. The later that somebody in time that somebody is diagnosed, then the worse the case is, and higher mortality rate perhaps. But what we have done here is we're trying to quantify that explicitly with numbers, with this stochastic Bayesian modeling that we're doing. So a good step then, further step beyond that would be to look at those conditional probabilities as well. So that's a very useful comment. Thank you.
Excellent. And I think you almost started covering it there, but is the increase in mortality from the delays in diagnosis the same across all ages?
No, it is not the same. But we quantified the delays in cancer, we quantified the impact of the delays in cancer diagnosis in two different ways. Now, in the Markov model, we are looking into the impact of cancer diagnosis at different age groups. So we haven't shown the results here. We only showed the results for age 47 in this case, but of course, the impact of delay is different for different age groups. In the earlier models, we didn't do it as part of the projection or anything. We are still using the fitted mortality rates, and average age at diagnosis is part of the variables explaining the data itself. So what we showed as an impact of the delay, 6-month delay or 12-month delay, is reflecting an average increase for all age groups, yes, but it doesn't mean that it would be the same for all age groups. That's why we just we are extending our study using Markov model as well.
Excellent. All right. So on the face of it, both the deprivation variation in breast cancer and the increase over time in female lung cancer incidence rates appear surprising to our anonymous attendee. Have you got any explanations for those?
Okay, that's another good point. Well, to start with, I'm not sure, and again, Aisha will correct me if I'm wrong, but for breast cancer, we haven't found significant deprivation differences, definitely not for mortality. But in any case, I think, well, we don't have the exact answers to this, the answer to this question. We don't know why it is, why the gap is actually increasing, why those differences are increasing. There are several thoughts there. We have been thinking about this, of course, but my take on that would be that access to care and access to screening programs is very, very important. I think we mentioned smoking habits, which have changed, and I'm not quite sure which direction they're changing towards when we talk about different deprivation groups. I wouldn't be surprised if somebody told me. I haven't looked it up, but I think perhaps Aisha has read more about this in several papers. But I wouldn't be surprised if somebody told me that the difference in smoking prevalence between different deprivation groups is also changing, is also widening. I wouldn't be surprised if that were the case, for example. That might explain part of it. But I would put together with the smoking habits, I would put, and that's the worrying part, if you like, from a social point of view. I would put the access to things like care and screening programs. I don't have evidence to tell you that this is the reason why it's happening, but it would be very worrying if that was part of the reason.
I can make a few more comments. So these there are a few factors, and these are not part of our data. So we didn't have a chance to confirm this empirically in the models. But for lung cancer incidence, for instance, smoking is definitely one reason. So there are some ONS surveys done regarding this issue. So in the models, we observed that most deprived deciles are experiencing higher lung cancer incidences, for instance, at the same time, higher deaths. And ONS surveys and data are confirming this point by showing that smoking prevalence in the most deprived deciles are 4 times more likely higher compared to the ones in the least deprived deciles, for instance. And regarding breast cancer incidence by deprivation deciles, so there are several polls in the medical publications, journals. The thing is, it seems like women in the highest deprivation deciles are experiencing higher stress, or the menopause period are postponing, and also childbirth is changing. Women in the higher deprivation deciles are having less children and at higher age groups. So these are thought to be linked to the breast cancer cases, one reason of higher breast cancer incidences, but at the same time, screening is more available, much easier to reach out for women with higher income deciles, So these are again contributing to the higher incidences according to the literature.
That makes sense to me. Thank you very much. I think we'll kind of tackle these next two questions perhaps in one go. So the first one is, do lung cancer projections make any allowance for past smoking changes? And on the similar topic, did you look at the difference in lung cancer incidence and mortality by socioeconomic group after controlling for smoking prevalence?
No, we didn't do this. It's a good thinking, but it was not part of our data, smoking prevalence or instances. So we didn't do this, but we know it has an impact because of published studies as well. Maybe we can consider this as a separate scenario by introducing a new variable, I guess.
I think that's also, just to add to that, we would love to do that, but we don't have the data. If any of our listeners there has a source of data, or they can talk to the ONS or whoever has the data to give it the same granularity of the data together with smoking habits for the same groups, that would be great. And it would be, I think, straightforward to include in our model. But as it stands, we don't have this data, I'm afraid.
Yes, that's quite often the case. I think we find that come up a lot. Lots more we could do with lots more data. I think we're coming towards the end, but we'll just take a final quick question. I think does the modelling take into account demographic changes that may occur in the future?
That's another good question. Quick answer is no. A longer answer is that, again, it's well, what you need there is a model within the model to try to predict what the demographic changes will be. We have thought about that also in the sense of age. Well, we mentioned before diagnosis, average age of diagnosis, and so on. So it's difficult when you project into the future. It's difficult to sort of adjust those variables for what is going to happen in the future. As I say, you do need another model within your model for doing that. But we have been thinking about that. I know that Aisha has started thinking about another project, and she's looking for funding for that. So if the IFO are interested, to look into projection of these rates in terms of socioeconomic factors and so on. But again, going back to the original question, the quick answer is no, we haven't included that in what we presented today.
All right, great, thanks very much. Well, I think that is pretty much all we have time for. So I think in the closing minute, I'd just like to thank Professor George Streftaris and Dr. Isa Arik for taking their time today to present to us, and everyone here for attending. Just quickly note that following today's talk on the 21st of October, the next webinar in this series will be presented, and Professor Andrew Cairns is back to talk to us about how to broadly use cause of death data to help us understand some of these mortality inequalities better. So do make sure to sign up for that one as well. And finally, a reminder that there will be a feedback survey following the closure of this webinar, and there will be a link on the email that gets sent out to you afterwards if you happen to miss that, closing the screen too quickly or something. So please do take a minute to fill it in. The feedback is very helpful when planning these events. So with that said, thanks everyone, and have a great day.
Okay, thank you.
Cheers.